I will say things of a mathy nature. Dear Father, we thank you for this day. I thank you for the students. Just ask you to bless this class, Lord. Help us to just learn what we need to today in the time that we have. In your name I pray, Lord Jesus. Amen. So I'm hoping today to kind of wrap things up for the most part for the material on test 2. And so we begin with, well, first of all, a reminder of what we mean by meromorphic. What's a meromorphic function? F is meromorphic on domain D if F is holomorphic, or you could say analytic, on D, except at isolated singularities of F, of which each is a pole. All right. So we'll talk more about meromorphic functions today. I just wanted to state that definition again. This is an important one to know because I might ask you questions about it. So if you don't know what meromorphic means, well, it's hard to answer questions about meromorphic, right? So meromorphic, certainly if you had a finite number of poles, of singular points which are of, not an essential singularity, if you had a finite number of them, then it's going to be meromorphic. You could even have an infinite number of singularities for your function and still be meromorphic, provided that those are isolated. Yeah.
So is it correct that an entire function, a function that's meromorphic on C might have an infinite number of poles, but a function that's meromorphic on C star can only have a finite number of poles?
A function which is meromorphic on C star could also have an infinite number of poles, I think.
I thought that was something that you used in the proof of one of the theorems. I think I found the proof of it on the math exchange. You used the definition of compact sets.
Well, let me just leave that as an open question at the moment. Can we have infinitely many poles for a meromorphic function on C union with infinity? All right, so I'm going to leave at the moment. I'm going to leave that as an open question. Sam says no, because there's some argument involving compactness. I'm tempted to believe him because I've got rattling around in my brain that the meromorphic functions on the extended complex plane are rational functions, and any rational function has a finite number of poles. So I want to believe, but anyway, I'm going to continue on with the notes at the moment. So we're to theorem 11.2.16, which I found a typo in the proof of, which I will correct momentarily. Let Z naught be an isolated singularity of F. Then Z naught is a pole of order n greater than or equal to 1 if and only if the modulus of F of Z tends to infinity as Z tends to Z naught. All right, so let's look at the forward direction of the proof here. Suppose we have Z naught as a pole of order n, right? Observe there exists G holomorphic at Z naught with G of Z naught not equal to 0, and f of z equal to g of z divided by z minus z naught to the power big N. Right? This is what we learned last time, is if we have a pole of order n, we can present it as an analytic function about the center point, such that that analytic function has a non-zero value, right, at the center point, and we divide by z minus z naught to the n. This is a presentation of a function which has an isolated singularity of, a pole of order n. We can do this, right? Then, all right, great, that's what we have to work with. Notice g of z, g holomorphic at z naught implies g continuous near z naught, right? Which implies that there exists m greater than 0 such that we can bound the modulus of g of z, modulus of z minus z naught less than some delta, right? I mean, there exists some delta greater than 0 such that we can bound, certainly we can bound the g of z to be less than a certain value because it's continuous, right? Then, thus, the modulus of f of z, right, is equal to the modulus of g of z divided by the modulus of z minus z naught to the power n. Admittedly, there's a algebra step or two there that I've omitted, right? So make sure you guys are on board with what I've written. I keep forgetting to give this back to you every class. I think I should give that. And then I think about it before class, I think about it after class, and then by the time I think about it after class, you're gone, which is fine. You don't have to stick around waiting for me to remember to do things. Anyway, there it is. Okay, so are we good on this so far? So in the notes, when I'm doing this, I have parentheses rather than modulus, which is unfortunate because, like, parentheses z minus z naught to the n could be a complex value. That wouldn't make sense. But the modulus is actually what's true. And of course, this is less than or equal to m over z minus z naught modulus to the n. This is, again, for what z am I making this estimate?
Wait, why are we trying to show that z is small? I thought we were trying to show it's large.
I'm approaching, we'll get there. We're approaching z goes to z. My point, though, is that the numerator is at most m. I mean, it's at most, it's,
Well, what we want to say is the numerator is greater than something.
All right, let's, again, just hold on a second. You agree this, right? I think so, yeah. And this is the kind of points we're interested in because we're approaching z naught, right? Points that are close to z naught, so modulus z minus less than delta. So my point is we can apply the inequality for the numerator there. And then what happens as z goes to z naught, given what I've underlined right here. Oh, what have I done? You're probably trying to argue me out of it. Oh, I'm sorry. Yeah. Dang it. Yeah. Curses. Man. I mean, what I've written is not true. It's just not the point, right? Yeah, thanks, Sam. I was about to argue squeeze theorem, but it's dumb. I'm not taking n going to infinity is the thing. Taking z goes to z naught. So let's just... So sorry. Hopefully I'll do better on the converse direction, right? So the point here is, if we look at, and that implies then that the limit as z goes to z naught of the modulus of f of z would be equal to infinity as g of z naught is, not equal to 0, and the denominator, to make this more rigorous, I suppose I should say that the modulus of f of z is equal to the modulus of g of z, right, divided by the modulus of z minus z naught to the n. And if you look at that, as z goes to z naught, the numerator tends to g of z naught, which is something non-zero, and the denominator can be made arbitrarily small. Therefore, the limit goes to infinity. We can make this precise with epsilons and deltas and stuff if you guys want to. It'd take me about 10 minutes. If you're interested, I'll do it in the help session today. How about that? All right. But to actually supply the epsilons and epsilonics to prove that that goes to infinity, I would need to, like let m be greater than 0, right? And then show there exists delta greater than 0 such that 0 less than z minus z naught less than delta implies that the modulus of f of z is greater than m. It's relatively clear that you can find such a delta because, we can use the continuity of g to make g small. Make g relatively close, rather, to the value g of z naught. And then we can make the denominator as small as we like to make that. We can choose a delta to make the denominator as small as we like, to make the quotient as large as we like. But again, it would take me about 10 minutes to really sort through those details. So if it's okay with you guys, I will allow this in the proof on the test if this is there. Sound good? So there's different levels of rigor that we can operate at, right? So I think this isn't too much of a sacrifice in terms of details. It's intuitively, it's not much of a jump to see that from this we get that. All right? Okay. Other direction then. Other direction. Can I erase? So the other direction here, so let's assume that the modulus of f of z goes to infinity as z goes to z naught. Well, I found a typo in my proof, but the larger stick in my eye was not apparent to me when I reviewed before class. Like the whole bounding by m thing is that's not even the point. Sorry about that. All right, so hence I say there exists r greater than 0 such that f of z is not equal to 0 for 0 less than modulus of z minus z naught less than r. Right, if it's going to infinity, you can't have values that are 0 close to that point, right? Because you need everything as you get closer and closer to the limit point to give you moduluses which are larger and larger. And if there's some things in there which are 0, they don't give you larger and larger moduli, right? So stands to reason that there should exist this r greater than 0 such that that is true. Hence, thus, we can construct h of z equals to 1 over f of z, right? Which is analytic for that disk of radius r centered at z naught. And what do you, moreover, h of z equals to 1 over f of z goes to 0, right? If we look at the modulus of h of z, 1 over the modulus of f of z. So if that goes to infinity, then 1 over it goes to 0, right? Using the interplay between limits at infinity and limits at 0, limits that go to infinity versus limits that go to 0, as we've learned since Calculus 1. What's that say about h of z near z naught? It's bounded near z naught, right? Because its value as we approach z naught is 0, and otherwise it's analytic on this disk, right? So that's everything. We know that, and think about it. So we've got z naught in the center, and it's analytic everywhere else in this disk of radius r, right? So it stands to reason at each point, I mean, the one place you could have the thing blowing up would be the center point, right? Otherwise, since it's analytic on the punctured disk there, we know that it's continuous at each point in there. So in sum, total, h of z is bounded near z naught, and what's that say? Right, therefore, z naught is removable singularity for h, and that implies that h of z is what? The sum n equals 0 to infinity of a sub n times z minus z naught to the n, using the Laurent, my definition of removable singularity. But what else do we know? We know that h of z goes to 0 as z goes to z naught. What's that say? That says that h of z naught is equal to 0, right? Which says that h of z is really what? The sum n equals n to infinity of a sub n z minus z naught to the n, rather n, for some n, because if it's got a, I mean, if it's 0, the 0 could be repeated, though, n-fold times, right? And so what does this give us? I mean, I should probably rewrite this a little bit more. Let me rewrite this a little bit. This is really, say, z minus z naught to the n power times b of z, where b of z naught is not equal to 0, right? Remember, we have this characterization of a removable singularity. We can write it as, well, the removable singularity, if we fill in the hole, we get an analytic function. This one in addition, we know that it's 0 at z naught, which means that we can factor out z minus z naught to some power, depending on what the order of the 0 is, which means that we could rewrite it as this for some n. Of course, that's assuming what? That h of z is not identically 0 near z naught. Why do we know h of z is not identically 0 near z naught? I think it goes back to the construction of h of z being analytic back here. You can't have that be 0 everywhere near z naught and still have h of z equal to 1 over f of z, where f of z is, you know, as advertised here. Okay, anyway, getting to the point. Therefore, What's 1 over, so what's 1 over h? F of z is 1 over h of z, right? And what's that equal to? It's equal to 1 over b of z times z minus z naught to the n. And what's that show you? Or maybe I should write it this way to sort of drive home the point better. It's got this function upstairs divided by z minus z naught to the n. The function upstairs, what's the value of b at z naught? B of z naught non-zero, right? So that reciprocal of an analytic function is analytic near z naught. And so there you go. That, by our theorem last time, is a pole of order n for f. So we've shown that the limit being infinity implies that there's a pole of order n. Es bueno? No? Yes? No? Well, we'll give you guys a second here to catch up with my talking. All right, so let's review. We have 3 kinds of isolated singularities, right? Removable singularity. If z naught's a removable singularity, then that says that our function, right, our meromorphic function, well, let's not. I need to talk about the global picture, right? So we will be dealing with some local to global initiatives today, by the way. So that's kind of exciting. We don't often get to talk about the local to global problem in math, but this is one of those days. But so z naught being a isolated singularity, if the values of the function are bounded near the point, it's a removable singularity. That was the first thing we proved. Riemann's removable singularity theorem, right? Then we just now proved that if you have a pole of order n, right? It's a pole of order n. That kind of isolated singularity, its signature behavior is that the modulus tends to infinity as you approach the point. And what does it mean to approach the point, for the modulus to approach? As z goes to z naught, what's that mean? Like, think about that. What does that entail? In the complex plane, if this is z naught, and we have z approach to z naught, along which path, right? All possible paths, right? So the modulus of f of z must go to infinity. To be more clear, you even have this, right? A straightforward consequence of this data is that if we evaluate that along any parameterization of a path, you know, so the limit as t goes to 0 of the modulus of f of r of t is infinity, right? And that's for any parametric path that goes through z naught with the parameter 0 matching up with z naught, right? All possible paths through the point must give us a modulus of the function evaluated along the path blowing up, right? That's a signature of a pole of order n. If you have a function which, you know, along one path it blows up to infinity, but along another path it doesn't blow up to infinity, if it goes to 0 or something, then that cannot be a pole of order n. So, you know, pole of order n, every possible path going through that limit point must blow up to infinity, because it's a genuine two-dimensional limit here. So let's look at an example where that doesn't happen. So while we're waiting for this thing to warm up, what do you guys think important concepts are for the next test? I think obviously the Laurent decomposition, right? The order of a zero, how we understand the order of a zero, how we capture the order of a zero in terms of the power series expansion, right? but more recently, the interplay between the order of a zero and the order of a pole, right? We have these nice theorems interlinking, like simple poles and simple zeros. Those theorems are very useful and important to understand. And if you look at those, I think you could actually prove those without too much trouble. Because what are the proofs of most of those involving? Not sure what's going on here. If you look at the proof of them, most of them have just been a straight calculation from the Laurent series. So they actually have been somewhat untechnical and very calculational. Some of those proofs are not too bad. This is the thing I'll be more precise about in the announcement I make sometime soon. Okay, guys? So example, did you already fix it? Okay, I'll trust you. I'm working. I have trust issues. But so f of z is, let's see here, e to the 1 over z has this expansion, right? And z equal to 0 is an essential singularity of f, because if you look at the Laurent series, it's got infinitely many reciprocal terms, right? That was our definition of Laurent series. Is if you look at the Laurent series expansion, definition of essential singularity. If we look at the Laurent series and we have infinitely many reciprocal terms in the Laurent expansion, then that's an essential singularity. And that's the case here. And look at how it doesn't fit. Look at how it distinguishes itself from the previous theorem we just proved. If you look at z equal to x, so just real z, what happens with 1 over e to the x? Well, 1 over x goes to what? As x goes to 0, from the positive side, we have 1 over a very, 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 very small. Let's see, wait a minute, 1 over something really, really small and positive is something huge, right? So this is like e to the infinity, which is going to infinity for positive x. On the other hand, I don't know why I mean, wouldn't it have been easier for me just to look at x approaching from the other side? Because if you go x approaching 0 from the 0 minus, right, if you go to really small negative values of x, what do you got? You have e to the minus infinity, right? What's e to the minus infinity limiting to? 0, right? So if you approach along the real axis from the other side, you get limit 0. So I get infinity from one side, I get 0 from another. If you look at z equals to iy, what's that? We've got that. Well, I times any real number, that's something on the unit circle, right? So as long as y is not equal to 0, 1 over y is just a real number. So e to the iy, e to the 1 over y times I is just a point on the unit circle, which has modulus 1. So along the imaginary axis, this thing limits to 1. Actually, from either side, I think. Actually, I'm not so sure so this is the funny thing, right? This is definitely not like, if you think about, this is a funny thing, right? Can you, the limit as y approaches 0 from the right, of e to the I times e to the I divided by y, right, does not exist. Because 1 over y is going to what? It's going to infinity as y goes to 0 from the right? So if you think about e to the I over y, you're going round and 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 round around the unit circle. It never settles down. It's just always spinning. But the thing is, we're not talking about e to the I over y. We're talking about the modulus of e to the iy. And that's always 1, no matter how many times you go around the circle as you approach infinity. So anyway, the larger point here is if we approach the limit point from different points, we get different moduli. Some of them blowing up to infinity, others limiting to a value. Yeah? Is that, you can see it, I hope. The Weierstrass Theorem says that if z0 is an essential isolated singularity of f of z, then for every complex number w0, there is a sequence Zn goes to Z naught such that f of Z naught n goes to W naught as n goes to infinity. And I mean, the example's not a proof, right? I found some that go to 0. I found the other ones that go to 1. I got another one that goes to infinity. So this theorem claims that you can find a sequence that will go to anything. If you pick me any complex number, you can find a sequence Zn that if you feed it to e to the 1 over z, it'll produce that value. It's pretty neat. The proof is down here, which I'm going to skip because we need to go on, but the proof is right there for you to look at. So then we should talk about isolated singularities at infinity. If f is an isolated singular point at infinity, what's that mean? That means that the reciprocal function, right, g of w is equal to f of 1 over w, has an isolated singularity at w equal to 0, right? Furthermore, we say that an isolated singular point at infinity is a removable singularity, a pole of order n, or an essential singularity if the corresponding reciprocal g, let's say, has likewise a removable singularity, a pole of order n, or an essential singularity. All right? And getting to the point here, what does a pole of order n look like? It actually looks like this. Bn z to the n plus dot dot b1 z plus b naught, and then plus a possibly infinite sum of reciprocal terms. This would give us, this is what a pole of order n at infinity's Laurent expansion looks like. Okay? The principal part of the expansion about infinity is the polynomial part, all right? And one of the things you can see from that is that if you subtract off the principal part, then you're just left with this term over here, which would then be analytic at infinity, as we studied when we looked at analytic functions at infinity in the previous chapter. Yeah. Here's some examples. I think there's an error in the last example in this section I want to talk about. Yep.
Why we have B naught in the principal part? I can't remember.
Let's see here. Why is B not in the principal part? That is a choice, and that choice will make the I think that will make the other piece of it go to 0 as z goes to infinity. That's probably the reason. Yeah, I'm not convinced that's supposed to be there.
The reason I was confused about it when I originally saw it is because the principal part in a pole at some other point.
Yeah.
The constant.
Really?
If I remember.
Yeah, we should be suspicious of that then. I will say though, like, I mean, do you see what I'm saying? If we do include the principal part in that, then that makes the piece which is analytic at infinity. But I think I said elsewhere I wanted the h1 of z. When we looked at the Laurent decomposition, that we had the f0 and f1. We wanted f1 to go to 0 as z went to infinity.
Yeah.
So the principal part here would be like the f1.
Yeah.
So that means we should put the b0 in the other piece. Because if this is the f1, and I want f1 to go to 0 as z goes to infinity, no, the other way around. So, okay, that's why b naught has to be in the, yeah, that's why b naught has to be in this part, I think. I don't know. You have question mark, okay, I'm not sure what to say about that without looking at a bunch of other things which I don't have in front of me at the moment. Okay. Certainly there is no doubt that everything up till the b naught is certainly in the principal part infinity. We're just quibbling over whether or not this should be in that side or that side in our thinking. Okay, so e to z has the Maclaurin expansion as you learned in Calculus 2, still the case here. So this has an essential singularity at infinity because we have, not just a polynomial piece, we've got it goes on and on. So e to the z is not is meromorphic on the complex numbers, but it is not meromorphic on the extended complex numbers because we have an essential singularity which is not allowed for a meromorphic function, right? Here we have p of z, q of z polynomials in the complex, degree m, degree n, respectively. I'm assuming that the degree of p is larger than the degree of q. So we can look at their quotient. The division algorithm, of course, gives us the existence of d and a remainder r, such that we can rewrite this like this. And the degree of the d is m minus n, right? And so this will form the principal part. And so maybe that's a reason enough just to make the language natural. Because if I didn't put the b0 in here when I was saying this is the principal part, I'd say like, hey, this is mostly the principal part except for the constant term, which goes over here with the other piece, right? So maybe that's reason enough. Name calling. So the principal part, d of z, doubling down on my bet that b0 is in fact supposed to be part of the principal part. I would be interested in the other place in the notes where I said otherwise. So, yeah. And I trust you that it is there because you're pretty careful and attentive to details. So, all right, so anyway, there's the principal part. There's the piece which is going to be analytic at infinity, all right? And so, in short, we have that this rational function is meromorphic on the extended complex plane because it has an isolated singularity of order m minus n at infinity, as is revealed by the fact that the principal part is a polynomial of degree m minus n. And then over here, when we look at the proper rational function piece of it, this has what? How many singularities are there for this? Well, it just depends on how q of z factors, right? But q of z is degree what? Degree n, so there are most n separate zeros for the denominator, and those are where the singular points are, all of which are isolated. So in total, we have at most n isolated singularities from this piece in the complex plane, and then an isolated singularity of order m minus n at infinity. So in the extended complex plane, we have just shown or argued that a rational function is meromorphic, because every singularity that it has is either removable or a pole of order at most some finite value. What I say in this is that if this piece is gone, if this piece is 0, in other words, if there's no polynomial piece, if you're looking at a rational function where the denominator polynomial has a degree strictly larger than the numerator polynomial, then that means that the singularity at infinity is removable. So, and you can just define, you can extend f from the complex plane to the extended complex plane by simply saying that the value of f at infinity is the ratio of the leading coefficients of the polynomials. So that's kind of nice. This, I think, a lot of what this example says is right. But I think one of the concluding sentence is wrong. And I want you to tell me why. So I say f of z is e to the 1 over z minus 1, all divided by z for z positive, all right? So if you look at that, we're subtracting off the 1 in the power series expansion of the exponential. It just leaves me with that. Then I divide by z, which gives me the, like so. Let's see here if that. I don't believe that. Come on. E to the 1 over z minus 1 should be 1 over z plus 1 over 2z squared plus 1 over 6z cubed and so forth, right? So if I multiply that by 1 over z, what do you get? We get 1 over z squared plus 1 over 2z cubed, 1 over 6z to the 4th, and so forth and so on. So I think there's a typo right here, right? That should be, this should be z squared, that should be z cubed, that should be z to the 4th, all right? Fine. Now, so now I do agree, hence the singularity at infinity is removable. Totally agree, because there's no polynomial part to the Laurent expansion. Centered at 0. And so we can, define, we can extend f to the complex plane by just saying the value at infinity is 0. Fine with that. But then I say this, oh, but this is what I disagree with. We may extend f to be analytic on the extended complex plane. The extended complex plane, why is this last thing wrong? I do agree that we could extend f to be analytic on the punctured plane with infinity adjoined. But what's z equal to 0 for this function? What kind of singularity is z equal to 0 for this function? Yeah, z equal to 0 is an essential singularity, which is not a pole, and therefore this function is not meromorphic on the extended complex plane, because 0 is an essential singularity. So sorry about that. I need to change the wording there. I wanted to confront that directly with you because, I'd like to make things correct. 11.4 really doesn't have much new in it. The main argument in here that's interesting is what Sam was claiming at the start of class, namely that, although not exactly in this language, but it's essentially equivalent, logically equivalent, although Sam might reject my terminology at the moment, a meromorphic function on the extended complex plane is a rational function. We have already shown that a rational function is meromorphic. So all that's left to prove in this theorem is that meromorphic implies rational. The way this is proved is really neat. Let's look at it. Okay. So if you have a meromorphic function, then the number of poles must be finite, otherwise, oh, here we go. Otherwise, they would accumulate to give a singularity which was not isolated.
Making that rigorous takes some real analysis.
So that's the real analysis that I've hidden, is to rigorously explain that. We need to look at relations between what is involved, compact and
Yeah, you need
open covers and so forth. Oh my. So we'll have to put that off until your next course in complex analysis. Sorry, guys. Or see Sam for the details of the sentence. All right. Now, if f is analytic at infinity, then we can define p infinity of z to be f of infinity. Otherwise, f has a pole of order n, which means that p infinity of z is a polynomial of order n. In both cases, f of z minus p infinity of z is analytic at infinity, and we'd have that f of z minus p infinity of z is going to 0 as z goes to infinity. I'm defining p infinity in this paragraph, if you're wondering. So I'm saying basically, what I'm saying here is let p of z be the principal part of the function which we're given at infinity. That's what p infinity of z is, all right? So it's either 0 or it's a polynomial of order n. Then, what else do we know? We can label the poles in the complex plane of the meromorphic function z1 through zm, right? And we could let pk of z be the principal part of f at each one of these poles. And that means that there exist constants alpha 1 through alpha n minus k, such that, for each pk, there exist these constants, that this is the principal part, right? So each principal part can be written as a finite sum of these reciprocal powers, right? That's the principal part of the Laurent expansion about any singularity. And by the way, also, as z goes to infinity, these pieces will go to 0, right? Okay, great. So what we then do is we let g of z be the given meromorphic function, all right, minus the principal part at infinity, minus the sum of the principal parts at each finite pole. So what we're doing is we're subtracting all of the evil, in some sense, off the. I mean, this is every singular piece of it. We're just subtracting those. And the neat thing is it turns out that g of z has to be identically 0. So g is entire because, g is entire because this minus this was analytic at infinity, and this piece is 0 at infinity, right? So that's why it's analytic at infinity. Any finite point, the difference between, at any finite point, this is just a polynomial, and this is the piece of the Laurent expansion which is divergent, so you're subtracting it off, and all you're left with is something that's analytic at near any singular point. And then, of course, at any point which is not singular, it's already analytic. So this function g is analytic everywhere. Moreover, g of z tends to 0 as z goes to infinity. And so it's bounded. And by Leibniz's theorem, we find that it's 0 for all z, which then proves that f of z is equal to a sum of its principal parts. And that is the partial fractions decomposition of the function. I mean, this is a rational function is the point. This is a sum of reciprocal terms and a polynomial. That's a rational function. Not just that, though. That's actually the partial fractions decomposition of the rational function. So it's a really, really neat argument that the reason it seems neat and untechnical is because I've hidden the rather laborious real analysis, which is needed to make rigorous this first sentence. The number of folds must be finite, otherwise they would accumulate to give a singularity, which was not isolated.
It's actually not laborious.
It's not laborious. It's just it takes background that we do not currently have. Yeah. Okay. Very neat, though. So this is the theorem that we have essentially proved. Every rational function has a partial fractions decomposition, and in particular, that partial fractions decomposition very much is based on the singularities. So the remainder of the section, guys, I have examples of partial fractions. Right? Here's one with. Let's see here. Let's just look at this for a second. This z cubed over z squared plus 1. I do the math. You're going to have what? A simple pole at infinity, because you've got one more than the denominator. So we're going to have degree 1 polynomial as its polynomial piece, which means it's got a simple pole at infinity. And we're also going to have poles at plus or minus I. But the math here, you've already done in previous courses. I'm not really doing anything new. There's the partial fractions decomposition. This is a global formula for f. All right. And this one, again, partial fractions. And other partial fractions. So let me get down here past. These are just, now this one's interesting. So this 1 over the quartic has this partial fractions decomposition. The beautiful thing about this is you can see what the singularities are for this function directly from that, right? You got a singularity at 0, and you got a singularity at 1. There's no singularity at infinity because there's no polynomial piece. I can also tell you that the pole has order 3. The pole has order 3 at 1 because this is the principal part. That's analytic at 1. On the other hand, it's a simple pole at z equal to 0 because this is analytic at 0. Then to find the Laurent series expansion, at 1, what do? I take this and rewrite it as a power series at 1. To find the Laurent series expansion at 0, this is already a Laurent term at 0. To change these into the proper thing, I have to expand these as power series about 0. I do all of those things in the next page of the notes. I find the Laurent expansions about both of the singular points for this function, either 0 or 1. And I would say that those are local results. They're both following from this global formula. Right? We can use this global formula to find local Laurent expansions, Laurent series expansions, which of course are based about a center point. And that's done here. And that's a lot like the homework that you did. Like here's the gory details. This is the Laurent series expansion about 0. I had to take those 3 reciprocal terms and do the usual geometric series stuff on it. There it is. Right. If an evil professor was to give you a choice, here's a rational function. You may find the Laurentic series expansion about one of its singular points. Which singular point should you choose for this example? 0 or 1? The answer is clearly 0, see, because to find the expansion about 0, all I had to do was take this 1 over z term and rewrite it like that, and I was done. That's the Laurent expansion about 0, just a simple geometric series, just 1. This polynomial piece is coming from expanding that about 1, which I do by adding 1 and subtracting 1.
So this is about 1.
This is about 1. About 1. The more complicated one was about 0, actually. Anyway, of course, we're out of time. I do have a handout for you guys. As I mentioned last time, if you already got it last time, it's great. If you didn't, it's because I forgot after you left. Who hasn't gotten this already?
Is it on Blackboard?
No.